Hi, everyone. Welcome to the fourth and final session of Program Evaluation and Intervention Studies. And this week we're going to look at our second causal model, which is the Interrupted Time Series Regression Model. So let's begin. Okay, for our agenda, for the first 5 minutes we'll do a welcome and overview. We'll identify the session objectives, discuss the importance of research design in improving regression models. For the first discussion, we'll look at interrupted time series. We'll discuss interrupted time series models and when to use, discuss assumptions and improvement over standard regression, and we'll review the benefits of being able to model multiple interruptions. For our second discussion, we'll do regression case examples. We'll demonstrate ITS examples, use the R package HAM, demonstrate how to interpret results, produce graphs to visualize results, effect sizes, and how to assess changes between interruption periods. And then finally, we'll wrap up and go over our final steps. Okay, so let's continue. Okay, so we've looked at differences last week, and it's a very powerful and helpful causal model. Not surprisingly, it won the Nobel Prize in Economics for its practicality and its power. But there may be times when we want to use something else because of the situation we're trying to model. So one reason we might want to use an ITS instead of a DID is if we suspect that we have a discontinuous effect after our intervention started. And so in this graph we have on the left the results from a differences study, where in this example we're looking at readmissions, 30-day readmissions. And on the right we have an interrupted time series study, and again it's the same data. We're looking again at 30-day readmissions. So on the left, how we can model that data is that we have in blue, we have the effect for our treatment group. In gold, we have the control group of trend. And we see that when we look at the results, we see a significant difference where our treatment group shows a reduction in 30-day readmissions. And we also see the control group, their rate increased. So we have in this on the left, we're just looking at pre and post data. So we have everything to the right of that green vertical line that represents when the treatment started. Everything is summed up in that where the blue line ends above that x-axis value of 1. And we may, after looking at some of our data more carefully, see that yes, there was an impact, but it did seem like our rate increased. So our interventions seemed to have an impact, but it wasn't immediate. We may have had a discontinuous effect. And how we can model that is to use interrupted time series. And we see that on the right side. So we actually have a blue trend line like we do on the left side in the differences study. However, we're going to break up that trend line into two segments. And we're going to look at the change in where that line begins after the intervention and the change in that trend. And so we're testing for this, in this time series, we're testing for a change in the intercept as well as testing for a change in the slope. And so you can see on the right side we have that blue line where it decreased at the time of the treatment, which we see with that green dashed line, but then went back up. So disappointingly, there may have been a situation where the effect didn't hold. One common explanation is the John Henry effect, where we know our staff tried really hard in the beginning to help the intervention go, but maybe that effect didn't hold. Maybe it just was a difficult thing to continue, or maybe just that one treatment by itself is not enough. There are other reasons, and we call them threats to validity. So that there are other threats to internal validity on our results, which, if we're using formative evaluation, this would be a great opportunity to, on the right side, to identify how we got our rate down that low, and why it went up, so that we would know how to keep that rate down. So when we have these situations and other situations that I'll describe more, the interrupted time series is a great way to model that data, because it's going to actually put those trends in there for you, and you can understand more about the change in the intercept and the change in the slope. Okay, so that brings us to more about what is interrupted time series. So let's begin on the top left, and we'll read through that to understand that and answer that question: what is a time series? Time series refers to a large series of observations made on the same variable consecutively over time. The observations can be on the same units, as in cases in which medical or psychiatric symptoms in one individual are repeatedly observed, or the observations can be on different but similar units, as in cases or traffic fatalities displayed for a particular state over many years, during which time the baseline population is constantly changing. In this chapter, and this is from the Shadish, Cook, and Campbell book, that is in the files. You can read through this. This is chapter 6. In this chapter 6, we describe a special kind of time series that can be used to assess treatment impact, the interrupted time series. The key here is knowing that the specific point in the series at which a treatment occurred. For example, the date on which a mandatory seatbelt law took effect. If the treatment had an impact, the causal hypothesis is that the observations after treatment will have a different slope or level from those before treatment. That is, the series should show an interruption to the prior situation at the time at which treatment was delivered. So if there's an impact, we should see, we could potentially see a change in the intercept, and I'll show you that in a little bit, and a change in the slope. So that's the benefit of the interrupted time series, that we can just narrow in on when that happened, because we're looking at a time series rather than a pre and post. We're looking at individual time points to help us assess the effect, what type of effect, and how big the effect was. So that brings us to describing types of effects. A post-treatment time series can differ from a pre-treatment series in several ways. First, there may be a sharp discontinuity at the point of the intervention, this time at which we expect the overall series to be interrupted. So we call it an interrupted time series. And when there's when we expect to see a significant change in our outcome, we refer to that as an interruption. We can also refer to it as a treatment period or an intervention period, but it would be when the treatment was applied. And we have another example for different types of effects. One of them being a discontinuous effect, which we showed in the previous slide, or in one of the earlier slides. An important thing to make note of is that we have different types of interrupted time series that we can perform. One, for example, is the simple interrupted time series, and this works when there is no control group. So as we look at the table in the top half of the right side, we see that we have 10 observations in the study design, and in between the 5th and the 6th observation we have a treatment. And you'll notice that this is just one row of observations, and that represents our intervention group. You'll notice that we don't have a control group, and that's okay, because that's one of the benefits of the interrupted time series, is that we can have A basic time series design requires one treatment with many observations before and after treatment. A design with 10 observations might be diagrammed as what we're looking at on the top right of the screen. But of course we would benefit from having a control group. So we see if we see lower in the slide, adding a non-equivalent no treatment control group time series gives us this display. Consider the addition of a control group time series to the simple interrupted time series design. The resulting design is diagrammed below. So on the top row we have our intervention group, our observations and treatment for our intervention group, and on the bottom rows we have the observations for our control group. And you'll notice there is no X on that between the 5th and 6th observations in that bottom row, because that's our control group. Our treatment is solely for our intervention group on the top row of this display. And again, this is from the Shadish, Cook, and Campbell book, Experimental and Quasi-Experimental Designs. And most of the photocopy slides here are from that book. Okay, so in a time series we can have different types of effects to that time series. For example, on the top we can see there could be a change in the intercept. Our first example of a simple interrupted time series has 180 observations and is nearly ideal for ruling out many threats to internal validity. And we see in this example, Cincinnati Bell, the telephone company, began charging 20 cents per call to local directory assistants. So if customers needed to talk to the operator for help, that would cost 20 cents. So figure 6.1 on the top right clearly shows an immediate and large drop in local directory assistance calls when this change began. And so if we look on the top right, we can see that the number of calls for directory assistance had steadily increased between 1952 and 1974. And we see that in 1974, when the change was implemented, where there's a 20-cent charge for each call, we see that that number sharply decreased. It went from about, I guess about 600 per day to probably about 150 calls per day. So that was a huge drop. You can see that if we use that vertical line right above 1974, we can see that going from that point forward, the intercept, which would be where that line starting at 1974 begins and touches that vertical line, we can see that that was a big shift and a change in the intercept. And so we can see that that number has slowly increased after that, but we would describe that change as the change in the intercept, because that's the most impactful change in that data that we're looking at. But we can also see a change in the slope. And figure 6.2 shows an example of an interrupted time series with 96 observations in which the outcome is a change of slope rather than a change in the intercept. And we see that starting in 1983. This is a cyclical pattern, so maybe there might be seasonality in this outcome. We can see it increases mid-year, I guess in the summertime, then decreases in the winter. Overall, we can see that the number changed, and it changed slowly. So we see a change in the slope. We still see that cyclical pattern, which isn't the main focus of this data, but we see that this intercept, the point where that 1983 data begins, doesn't really change a lot from where we would expect it to be at. So there's not a change in the intercept like we see in the graph above, but we do see a change in the slope. So we see that it starts to increase. And so the trend or the slope is what the difference in the previous data that we're noticing. So it's not a change in the intercept. It doesn't shift up or down on that on the y-axis that we see for that vertical line at 1983. Instead, we see that overall trend heading up. So it's we call that a change in the slope or the trend. And then on the bottom, we have an example of weak and delayed effects. Although interpretation of figure 6.2 is not as clear as interpretation of figure 6.1, few simple interrupted time series designs are even as clear as figure 6.2. Figure 6.3 represents a more common example. It includes 63 observations, and the effect seems both delayed in onset and weak in strength. So when we look at that labor law date, about December of 1989 or November 1989, we see that vertical line that starts about November 1989. When we look at the change, it doesn't look a lot different. Impact begins around January 1990, and we see that the change is not a big change in the intercept and not a big change in the slope, but overall there is a slight change there. So we'd call that weak or delayed effects. And what we can actually see is that another example, I don't have it in the text here, but another example that you might see is what we would also call weak and delayed effects would be if we had just a flat trend, but then it to gradually pick up, like it's picking up steam. We don't see that here, and the authors suggest that kind of delayed effect, that it's flat in the beginning, but then is more incremental over time after a certain point. That would be that's also another example of weak or delayed effects. You could see an incremental change, but you don't see a big change until later on. It's gradually increasing, but it's not a significant amount until later. Although the authors did say that's rare. So, but what we're looking at on the bottom right screen is more commonly found for weak and delayed effects. I just wanted to show this slide again. You'll notice that we have different types of trends, and they're similar to what we just reviewed. For example, on the optimal side, it has an immediate change in the intercept as well as the slope. It changes right after the intervention started on the level for where that line would be at for the y-axis, and then it continues to grow. So there's a continuous effect where we, after immediate shift in the intercept, we see that it just keeps going and going. So there's ideal or optimal improvement, and what we call a continuous effect if that effect still keeps going and we still see that change in that slope. In that very first slide I showed, it was a discontinuous effect where there was an immediate impact, but then it just the effect wavered. And then on the second slide we see that immediate effect where that effect happened and just maintained that rate. Okay, so here's an example of a psychiatric crisis intervention and removal study. So the intervention began and was removed 6 months later. So on the right we can read that figure 6.8 shows an example with 36 observations by Redding and Ralphson in 1995. In October 1989, a psychiatrist was added to a mobile crisis intervention team to provide immediate on-the-spot psychiatric treatment in hopes of preventing subsequent state hospital admissions. This effect occurred. 6 months later, several factors led to the termination of the psychiatrist services, which led to a rebound in state hospital admissions. Although not pictured, okay, so let's just review what that is on the graph. And we see that they started an intervention with a mobile psychiatrist to help reduce state hospital admissions. And we see that in that first vertical arrow on the left. We see that would have been in, let's see, it says October in 1989, but that okay, so we see that the biggest impact is right in that first arrow. We see a drop, and then 6 months after, we see that where that second vertical arrow's at, we see that the intervention was removed, unfortunately. And so maybe not surprisingly to the staff and stakeholders, that intervention or that state hospital admission rate jumped back up. So we can see the intervention began, it improved, showed improvement on our far left, had the biggest impact where that first arrow's at, and then unfortunately the psychiatrist services were removed, and that hospital state admission rate jumped back up. So we have two interruptions in the data. The first is maybe full implementation of the program with that first arrow on the left. And then we have another interruption. Although it's not a treatment, we can't call it a second treatment because they removed the treatment, but we can use that more generic term of interruptions. And we see in those two interruptions, they had their best performance, but unfortunately, after it was removed, their hospital readmission rates jumped back up. So, but the benefit of this method is that you can put in two interruptions, and what we can do is see, okay, well, how big of an impact was there after that first arrow? We can calculate that. We can see what the effect size is there. And then, that although it's an unfortunate change in their policy, but we can see that after removing the treatment, we can test that effect and use that as to help support our argument for cause and effect. We can say that we were at a really low hospital admission rate, and by removing that impact or removing that intervention, it led to an increase in hospital state admissions. So we can show the impact of including an intervention, but we can also use the impact of removing an intervention. So if you looked at research study design books, you might see an X, a solid X, and then you might see an X with a slash through it. That slash through it is what that second arrow is. That's removing your treatment. And so that would be how we can test it with the interrupted time series. Okay, so let's just review some strengths. We see that we can use ITS when we don't have a control group. And for example, we might want to test a policy that we have across all of KP. So there may be many situations in which we just don't have a control group because at KP we have that one KP approach, which I guess we don't always implement everything across. But if you wanted to test a policy in which, or some intervention or some practice in which everybody in your population is now exposed to whatever that intervention or treatment was, or that big change, you don't have a control group, you can still get what we call a counterfactual from an and interrupted time series analysis. So you can test cause and effect with only the treatment or the intervention group. ITS works with individual level or aggregated data. I'm going to use aggregated data in the example section. We can also use on dichotomous outcomes such as readmissions or mortality or infections. We can use ITS when parallel trends fail for repeated cross-sectional differences and differences. If we wanted to try to do something more like a time series with differences and differences, it's a little bit more susceptible to the issue of parallel trends with that pre and post. We don't have that issue, but if we wanted to do like more of a time series with differences and differences, we may find it just more convenient to use an interrupted time series. But for both, what we can do is if we do have a strong strong evidence for parallel trends for that assumption being violated, what we can do is grab a subsample of similar groups that are similar in their baseline outcome scores, and we can use them as a subsample for our control groups, and then we can do our analysis that way. And I'll do an example of that later. And ITS is proposed as a more flexible and rapid design in health research before defaulting to the traditional two-arm randomized control trial. ITS can accommodate design variations in which the effect of multiple treatment periods are of interest. For example, the researcher may be interested in studying the effects of an intervention that is introduced, withdrawn, just like our last example, and reintroduced, or an intervention that is followed by a separate intervention at a later point in time. So we can, if we have our intervention, it's introduced and then removed, we can test that way. Or if we have an intervention in which maybe part of it is implemented in phase 1 and then the full or the intervention plus is introduced at a later time, we can test that way. And we also assume that any time varying unmeasured confounder is relatively slowly changing and would be distinguishable from the sharp jump in the intervention indicator. In other words, unobserved time invariant confounders probably don't have the same impact as time varying X, which likely to have gradual changes. In other words, we really want to focus on our post-intervention slopes. We can see how big of a shift. Are we seeing something that may be due to time varying covariates, things that change over time, or are there things that are just consistent about our patients or our hospitals that don't change over time? We can view our slopes post-intervention to see what kind of change are we looking at. Okay, we do have some limitations. These are more or less frequent problems with interrupted time series design. One is just there are really two reasons we might have problems. The first is that we see in the first couple of bullets is just trying to model how that change happens. It's a lot easier if you're working with differences and you can say, oh, we had a change after the intervention. But when we get into how does that change look like? Is it kind of rapid? Is it slow? Is there an immediate change in the intercept, or no change in the intercept, but a gradual change that we see incrementally? That's kind of one of our tougher things to model. Not impossible, but just something that we have to be careful about when we design our studies. And the last couple bullets refer to just the issue with trying to get enough data. It does mention 100 observations, 100 time points are recommended for statistical analysis, but That's a really high number, and we may not need to do that if we feel like the period we expect to see change is within a year or two. So if we expect that change happens, if 1 year is clinically relevant, then what we can do is get 1 year of post-intervention data and maybe 1 or 2 years pre-intervention. So, and because it's a time series, we can look at it month to month. If we're looking at change that happens monthly, then yeah, you can probably get more than 36 data points. You can probably get 50, 60. You can just maybe a 1 week period is something that makes more sense. So if change happens rapidly and right away, then you can probably change your unit of time from months to weeks. And then it also mentions just trying to get the data, but it's a little bit easier now. I think probably when the book was first written, it was more of an issue. And the second edition came out in 2001, so I think that's maybe what still in the hospital system, we do get a lot of data compared to many other fields even today. So it's maybe not as big of an issue in healthcare. Okay, so let's begin our first examples on interrupted time series. We're going to look at the California cigarette sales tax, and we're going to use control groups as well as no control groups. Okay, so let me begin with the introduction. California's 1989 cigarette sales tax. 1988, voters in California passed a 25-cent sales tax on each pack of cigarettes to help reduce smoking. Smoking had slowly become less frequent in the U.S. over the years, and so that leaves us with the question, did the cigarette sales tax actually help? ITS works for single or multiple groups, for single or multiple interruptions, i.e. treatment periods. And we see this data ranges from 1970 through 2000. It's in the Linden article that can be found in the files section. So here's some of the data and some of the results. And so we're using a simple interrupted time series. In other words, there's no control group. So on the left we have our graph, and it reads as cigarette tax for California. And so this is just our intervention group, and we're just looking at California. We're going to compare it with, we can compare it with all the other states. But in this example, we're just going to look at California's results. Maybe all states, that comparison's too big, but so we're going to go ahead and start with our California example. You don't have to do a single interrupted time series whenever you do a multiple interrupted time series, but we're going to show both in this example. Most authors just choose one or the other, but we'll do both. And so on the right side we have our interpretations, and this came out of the HAM package for both the graph and the interpretations, and I just pasted it in here. And so that in the graph we have in orange, that's California's trend. We have a counterfactual, which you see as a dashed line on the right side of that blue vertical line, and that blue vertical line represents the treatment period, or the start of the treatment, and that's its 20th year, so that's 1989. And that dashed line represents the counterfactual. So if there was no intervention, then what we might have seen for the trend for California is that it would have continued down, like the trend would have continued downward like the rest of the United States, and it may have continued along that dashed line. And so we see that there's a second solid line, and that represents the actual data for California after 1989, or that 20th year that we see on the x-axis. And we have cigarettes sold, and these are packs per person for the entire population. So within a year, if you're to average out the number of cigarette packs sold to Californians, starting back in 1970, was about 134. So that's our intercept. So let's go to the top right, and we can read the intercept as 134 packs sold, and it's the starting value of the trend for the intervention group. So we're starting at 134 packs in 1970, and we see our next variable, ITS time, is negative 1.78, and the slope prior to the intervention. The coefficient is significant. When we have a negative slope, that means our trend line is going downwards, and we know that trend was significant. So if we look at our graph, ITS time equals negative 1.8, and so that's a very significant result, and we know that because we have those 3 asterisks, and if we go down to our p-values, that would indicate our p-value, our chance of a type 1 error, is less than 0.001. And so if we go to post 1, we see that's the change in the intercept. And post 1 is negative 20.1, and the immediate shift in the trend line after the intervention start. For example, it's the first year of the intervention. The coefficient is significant. And we look at the significance, see those 3 asterisks. So we know there's a very low chance of being wrong in our interpretation of that. And so we go down. So that's the change in the intercept. So we know that there's at least an immediate impact in, if we think about the type of effect or change we're seeing a change in the intercept. We're seeing it's very significant, and so what we want to do next is look at our change in the slope. So that's what we're going to do. How we'll interpret the next coefficient, TXP1. That is negative 1.5, and the difference between pre and post intervention slopes, it's the change in the pre-intervention slope. The coefficient is significant. So we see that there's a slope for that intervention line before our intervention starts, and it begins at that intercept and goes to about the 19th year. And we see that solid line after the intervention start even becomes steeper. That trend's going downward at a steeper rate. And so we want to know what the difference is in that change in the trends, and that's negative 1.5. So there's an additional 1.5 packs of cigarettes, or 1.5 packs fewer cigarettes being sold in California year after year. So we know that's the change in the trends between before and after that intervention started, before and after that sales tax, and we see that's also a very significant result. That p-value is less than 0.01. So in summary, the results show that after the start of the intervention, there was a significant change in the cigarettes trend. This gives a total post-intervention trend in the cigarettes of negative 3.27. So in other words, the total combined value of change, not the change relative to the pre-intervention. So we see that, so if you add the trend or the slope for both periods, we have negative 1.8 plus negative 1.5, and that's about negative 3.3. So overall, we're seeing that there are 3.3 fewer packs of cigarettes sold per year in California since 1970. So that's a big change. Okay, but again, we can get this in the ham package. You can get the graph and the interpretations, and you can get those. Or if you want, you can just use this slide and use my interpretations. And And if you wanted to plot your own graph, you could just plot it like that, like how I have it on the left side, and you can use it as a template for your own work. Okay, so in this slide we're going to look at our California sales tax example again, but this time we're going to use a subsample. We're going to compare California with Colorado, Idaho, and Montana. And we're using these three states because they started at similar levels as California. So we have we also now have 2 intervention periods, and you'll notice that there are 2 blue vertical dashed lines. And we now have a control group. Our control group is in purple. Our line is in orange. That represents California. And so let's just compare it with the single group example, or the simple interrupted time series. We just have 1 time period, and we just have our intervention group California, but in this we have a control group that we see in purple, and we have 2 intervention periods. And we're going to compare California with Colorado, Idaho, and Montana because they started out at similar levels for the cigarettes sold per person. And on the left, we do have this graph that comes out of that comes through the ham package, and on the right, we do have just kind of our main interpretations. I do have all of them in the next slide, but there are 12 coefficients, so I'm going to limit it to just the main 2 and our interpretation of the overall results after the first intervention period or interruption and after the second interruption. So let's go ahead and begin. So we see IXP2, which I have circled, is negative 13.7, and the difference between the intervention and control groups, it's intervention minus the control, in the period immediately after the second intervention started. So this is the first year of the intervention 2, the coefficient is significant. And so we have an interruption at the 13th year. So I think that's 1982. There wasn't really an intervention at that point, but the author suggested using an example of a previous period that there may have been some change. So this is just to show more or less how interrupted time series can handle 2 interventions. There wasn't really an intervention at that period, but we're going to use that just so we can show how and explain how we can use 2 interruptions in an analysis. So we see that first intervention, but now we're looking at the second intervention, and that's IXP2. And so what that means is we're going to look at the trend between our control group and our intervention group. We're going to see the change in the intervention group's trend minus the trend change for the control group. So we're looking at the intervention trend minus the control trend, and the number you get is 13.7. So we see that purple line prior to the second intervention is very close to that purple, where that purple line begins, where the second intervention begins. We see that blue dashed line. There's not much difference between there. So the change in their trend is about 0. And then when we look at the where that orange line ends for in that middle period, we see that it's about where the control group's at, but the intervention after that second intervention takes a big drop. And so that's about, I guess, maybe 14 points. And so if we were to subtract the change, or the intervention trend change minus the control trend change, 14 minus about 0. The number we're left with is 13.7. So that's the difference between those. And that calculation probably sounds familiar when we think about differences and differences. And it's the same idea. We're going to subtract the intervention time post time minus the intervention pre-time. And then we're going to subtract control after minus control before. And so that, if that sounds familiar, that's exactly how we do a differences and differences when we just have 2 time points. So we can kind of think of that as a differences and differences between the intervention and control at that second interruption. Okay, so that tells us, and we see that p-value is less than 0.05 because we have that one asterisk. And then so now we're going to look at our second main variable. That's txip2, and that's negative 3.8 and significant. This is a difference in both group slope changes since the first intervention slope compared to the second. For example, both have first intervention slopes of 2 and the control group slope remain the same. Therefore, the second intervention slope is 0. And the intervention group slope decreased by 2, then txip2 equals 2. This for example part is just an example that you'll find in all the output, but I just wanted to show how those calculations are done. And it's very similar to the same idea that we had with the change in the intervention, as well as how we look at the differences and differences effect. We're going to compare how the slopes changed for the intervention and control group, and then we're going to subtract that difference between the two, and that gives us negative 3.8. So that because it's a negative value, that means that the intervention group, their slope decreased 3.8 more packs than our control group. So we have 3.8 in terms of our slope. There's been a big drop by about 4 more packs in California versus the rest of these 3 states. So there's a bigger decrease for California than the other 3 states. So now we can read the summary, and we see that for the first summary, that represents what we're seeing in that middle period between the 2 blue vertical bars. For the first intervention period, the results show that the intervention group's significant shift in cigarettes post-first intervention was negative 3.8. The control group's significant shift in cigarettes post-first intervention was negative 5.31. The non-significant difference between both groups is 1.5 packs of cigarettes. So we can actually see that there was a bigger change in the control group's trend after that first intervention period. Both states show a decreasing trend in that middle period, but those 3 states had a steeper decrease, but not significantly. So we'll look at the summary for that last part of the graph, everything to the right, starting at that second blue dashed line. And we see that for the second intervention period, the results show that the intervention group's significant shift in cigarettes post-second intervention was negative 3.3. The control group's significant shift in cigarettes post-intervention was negative 0.99 or negative 1. The significant difference between both groups is negative 2.28 or 2.3. And so we see that when you look at the difference between those intervention periods and the change overall, there was about a change in trend of about 2.3 packs per person in California. So that's still a significant trend, and we can see that circled in red, there are 2 asterisks there, so that's there's less than a 1% chance of being wrong when we're saying that there was a significantly bigger or a significantly larger decrease in packs sold in California. Okay, so here are the full set of interpretations. You'll see there are a lot of them. I still only use 2 variables to create all these different coefficients. It was which states are our intervention, which are our control, and also when the intervention began. And we have a time variable that would be our second variable. So we have a variable that indicates which group they're in, the intervention or control. We have a variable that indicates what month it is or what year it is in the data. And then we also add into our into the ham package when those interventions or those interruptions actually happened. So the ham package creates all 11 variables based on just 2 variables and when the intervention happened. And so you can see that here's some example data, and we can see that all of these variables get created for you. And you can see that what makes this interrupted time series difficult, as we have more interruptions and we use both our control and treatment group, is that some things get coded very differently. So I just have an example of the difference between our intervention group at the top and our control group at the bottom. And you can see that, just to show you that how these values get calculated, and that they do get calculated. Okay, so in summary, we can use ITS when we have no control group, but we still get a counterfactual to test the causal effect. ITS lets us break up trends into smaller periods. We can then test change in intercepts, slopes, and so on. If we think back to that very first example where the trend seemed to help right away, but the impact of that program kind of lessened or weakened over time, we can calculate that and test those trends. ITS can help estimate shifts in trends, a good alternative to difference in difference when it seems like something's in the data. The slides with the graphs and interpretations can be templates for future studies. Use ham to create interaction variables and run as a standard regression in R, SPSS, SAS, Stata, and so on. So you can just run the data, have all those interactions and variables created for you, and then you can proceed in whatever statistical package you're most comfortable with. And we have an example in the appendix. First, we have just some more definitions on what type of effects we may see, and then we have an example of multiple interruption periods for Louisiana's drunk driving study in 1973. So thank you, and thanks again for watching this. Thank you.